Welcome to this session where we'll be discussing the absorption and intensity shifts that are happening in UV spectroscopy. So there are two absorption shifts which we usually observe and two intensity shifts which we observe in UV spectroscopy. The absorption shifts, the bathochromic and the hypsochromic shifts are usually the absorption shifts, and the hyperchromic and the hypsochromic shifts are usually the intensity shifts. So we have a graph here which represents the molar absorptivity or absorptivity versus the wavelength. The wavelength which I have chosen here is from 400 to 800, that is the visible region, starting from blue end to ending up till red end of the spectrum. So we find all these four absorption and intensity shifts in this particular diagram. So let me go for the absorption shifts first. In that, the bathochromic shift, here you can see the bathochromic shift is the shift in the peak towards the longer wavelength region, also known as red shift, because the peak or the peak maxima tends to move towards the red end of the spectrum. So what are the reasons? We'll discuss in detail in the subsequent slides, but just to brief you about the reason that is responsible for bathochromic shift is if you add auxochromes that are having the n or the lone pair of electrons. If you have a lone pair of electrons, then the transition is from n to pi star, and if any molecule that is enhancing this n to pi star transition, then we usually see this bathochromic shift or the red shift. There could be one more reason, that is the change in the solvent could also bring about the bathochromic shift. So this bathochromic shift is one type of absorption shift. And there is one more absorption shift known as the hypsochromic shift. Hypsochromic shift is also known as blue shift because the peak maxima is moving towards the blue end of the spectrum, that is towards the shorter wavelength region. So also known as blue shift. So what would be the reason that are bringing about the blue shift? The reasons are exactly vice versa of the bathochromic shift. Here the removal of conjugation or change in polarity of the solvent. These are the two important causes that bring about the hypsochromic shift in any given molecule. We will go in detail about the hypsochromic shift in the subsequent slides. So these were the two absorption shifts which we observed in the UV spectroscopy, and the next are the intensity shifts. The first one is the hyperchromic shift, and the second one is a hypochromic shift. So what are the reasons for bringing about the hyperchromic shift, or what are the reasons that are bringing about hypochromic shift? So hypochromic shift is usually observed when there is increase in the absorption, or when there is an increase in the electronic richness, or when there is increase in the conjugation. If I add, if I tend to add more of the auxochromes as I did in bathochromic shift, if I add the auxochromes to the molecule, they tend to show hyperchromic shift along with bathochromic shift. Okay, so hyperchromic shift is defined as increase in the absorptivity, increase in the molar absorptivity of the molecule that leads to hyperchromic shift, and the basic reason is the increase in conjugation or addition of auxochromes. And coming to the next intensity shift, that is hypochromic shift. Hypochromic shift is the decrease in the absorptivity or the molar absorptivity of a molecule because of some geometrical distortion in the molecule or removal of any group which is decreasing the conjugation. So hyperchromic shift and hypochromic shift, they are exactly vice versa. Some kind of geometrical distortion if you bring about in a molecule, then that may lead to hypochromic shift. Hypochromic shift is nothing but decrease in the molar absorptivity. So this hyperchromic and hypochromic shift are also known as intensity shifts because there is increase or decrease in the intensity. Decrease, that is hyperchromic, or increase, that is hyperchromic shift. Decrease, that is hypochromic shift. So coming to the next slide, where we will discuss in detail about bathochromic shift. Bathochromic shift, as I just now mentioned, a shift of band to lower wavelength longer wavelength region or lower energy region due to the presence of an oxochrome, or also because of the solvent effect. This is also known as a red shift. And I just mentioned hypochromic shift is again an absorption shift, where a shift of band towards higher energy or shorter wavelength region, also known as blue shift. Hyperchromic and hypochromic are the intensity shifts. Hyperchromic is an increase in the molar absorptivity. Hypochromic is decrease in the molar absorptivity. Coming to bathochromic shift, I just now mentioned, it is the shift of band towards lower energy or the longer wavelength region because of the presence of oxochromes, and the oxochrome could be the OH groups or the methoxy group that tend to increase the conjugation. We have an example here. I have taken this paranitrophenol in alkaline medium, and this paranitrophenol in alkaline medium shows a red shift. That is because the negatively charged oxygen here delocalizes much more effectively than the unpaired or the unshared pair of electrons. So compared to the phenol OH, this O- will tend to increase the charge and the delocalization, so that this molecule as a whole behaves as a very electron rich molecule. So you can see the paranitrophenol had lambda max of 255 nanometer, and once it was taken in the alkaline medium, the lambda max shifted to 265 nanometer. So basically there was a shift in the wavelength from 255 to 265, almost 10 nanometers. So that was because that was attributed to this O- ion, which was delocalizing electrons more effectively than the unshared pair of electrons which were present in the paranitrophenol. So coming to the hypochromic shift, is, as also already mentioned, the effect is due to the presence of an group that is because that causes removal of conjugation or by changing the solvent polarity. I have taken an example of aniline here that shows hypochromic shift, also known as blue shift, in acidic medium as it loses conjugation. Here is an aniline which is taken in the acidic medium. You can see it is turning to a salt. So basically it is losing the electrons, and there is a loss of conjugation here. So the lambda max, we call it as the absorption maxima. It is rather from 280, it is coming back to 260 nanometer or the lower wavelength region. This is because of the loss of conjugation of this aniline in acidic media. And we have one more example of this is the hyperchromic shift or the intensity shift we'll be discussing here. If oxochrome is introduced to the compound, the intensity of absorption increases. As I mentioned, the hyperchromic shift is a shift in the lambda max or shift in the molar absorptivity. So I have a pyridine here. To this pyridine I have introduced an oxochrome. Oxochrome is nothing but the compound which is rich in electrons, and this by itself does not have any absorption, but when attached to an chromophore like pyridine, it increases the absorption. Okay, that is the definition of the oxochrome. So we have pyridine, we have 2-methyl pyridine, and if you see pyridine, the molar absorptivity of pyridine is 2750, and the molar absorptivity of 2-methyl pyridine is 3560. So basically it is the increase in the molar absorptivity from pyridine to 2-methyl pyridine that was because or that was attributed to the introduction of a methyl group at second position on this pyridine. We call this intensity shift towards the higher absorptivity values as the hyperchromic shift. And we can also see there is an bathochromic shift, a sort of bathochromic shift which is happening, or shift in the absorption maxima towards the longer wavelength region. You can see it is from 257, the pyridine had 257 nanometer as a lambda max or absorption maxima, it shifted to 260 nanometer because of the introduction of this oxochrome. So the hyperchromic shift are usually attributed by the introduction of the oxochromes. Coming to hypochromic shift, also known as it's a type of the intensity shift where the molar absorptivity is coming to lower values. When absorption intensity or the absorptivity of a compound is decreased, it is known as hypochromic shift. And we have an example here, naphthalene and 2-methyl naphthalene. So naphthalene is having a molar absorptivity value of 19,000, and 2-methyl naphthalene, an introduction of 2-methyl or methyl group at second position, the molar absorptivity drastically reduced to 10,250. So basically that was because of the geometrical distortion of this naphthalene structure. So we studied in the previous slide that if there is a geometrical distortion in the molecule, that will reduce the absorption intensity, or that will bring about a hypochromic shift. So these were the kind of shifts which are evident in UV spectroscopy. I'll just try to recollect the slide which I have shown previously. Yeah, so we had two absorption shifts. The first one is the bathochromic and the second one is hypsochromic shift. Bathochromic also known as red shift, hypsochromic also known as blue shift. And bathochromic was because of the introduction of the oxochrome that led to the shift of absorption maxima towards the longer wavelength region or towards the red end of the spectrum. Hypsochromic is the removal of conjugation or removal of the oxochrome or change in the solvent polarity that led to a blue shift or hypsochromic shift. Here the peak will shift towards the shorter wavelength region or towards the blue end of the spectrum. Coming to the intensity shift, that is hyperchromic shift. That is hyperchromic shift is increase in the absorptivity values just by either increasing the conjugation, or the second type of intensity shift is the hypochromic shift, which is the decrease in the absorptivity values because of geometrical distortion happening in the molecule due to introduction of a new group. We took as an example of naphthalene here, where in which there was a geometrical distortion. I'll go to that slide, where there was geometrical distortion by the introduction of this 2-methyl group. So these were the different types of absorption shifts and the intensity shifts that are happening in the UV spectroscopy.